semiconductor chips have been at the tip of the spear in going through transformation due to geopolitical tensions today. Let's start with you. Can you explain why that is?
Yeah, thanks, Andrew. And Saeed, great to be here with you, old friend and colleague. As Andrew, we've discussed in some other episodes that semiconductor chips are really the new oil that fuel the modern economy. More than oil, though, because they are always constantly changing and evolving at a very fast pace. But we are using so many thousands of chips in our different products that we're all reliant and dependent on. And it's, to me, the ultimate enabling foundation technology, without which no other technology can really come alive and work. And what has happened in the last 40, 50 years in this era of intense globalization is that different parts of the world have become competitive in different parts of this very intricate globalized value chain. And as a fallout of that, some of the parts of the value chain have become really concentrated, and that has created what we call choke points in the industry that I think governments around the world and industries getting to be really concerned about. So as an example, and as one of the most important examples, almost entirety of the high-end node, and we're going to talk about this, very cutting-edge technology chips are manufactured in Taiwan. And almost 75% of all chips actually are manufactured in the Asia-Pacific region. And as we know, this region is fraught with geopolitical tensions today, other than the other natural disasters kind of possibilities. So we really have everybody's focus right now on creating more resiliency and less dependence in this area. Saeed, maybe you can pick this up and talk a little bit about what are chips and why are they so complex?
Yes. So you're absolutely right, Kirti. Chips are becoming a very integral part of our daily lives. And these components are used in a wide variety of applications, from consumer electronic devices to hardware that's used by enterprise to data centers. And it used to be that chips were used for specific, more compute-intensive applications, but now chips are everywhere. And some of the mechanical devices are becoming more electronic devices. For example, automotive, you take a car, it used to have few chips. When I started my career in this industry, now we find hundreds of chips, in some cases thousands of chips in a car. And car is now, it used to be a mechanical device, now it's pretty much becoming an electronic device. And then in our daily lives, whether it's your cell phone, which can have hundreds of chips, to coffee maker, which can also have chips. So it's becoming a very integral part of our daily lives. And it's the innovation in chips that's driving the overall technology landscape.
Let me jump in here for a second. Say, how are these semiconductor chips actually made? Can you walk us through the different steps in the process? And also, I wanted to ask, how many companies are involved and how many countries are involved with this?
Yes, that's a great question. So first of all, building on what I just said, the chips are used widely in our daily lives. And to just make a point about this, last year, there were 1.1 trillion chips shipped. And I think that's, if you divide it by the population of Earth, I think that comes out to roughly 150 chips per person. And obviously, it's going to skew if you are in a developed country versus in other regions. So it's very widely used, trillions of chips getting shipped.
No other product in the history of the world has reached this volume. No other product.
That's really incredible. That's a great point, Kirti.
Yeah, it's the most manufactured thing in human history. So I think there was an article that talked about 13 sextillion chips have been manufactured so far in human history. Now, coming back to your question, Andrew, how chips are manufactured. Chip manufacturing is one of the most complicated and advanced manufacturing process. I'm oversimplifying it. Hopefully, some of my electrical engineering friends don't get offended by it. It just starts with what we call it wafer fabrication, where wafers are made using silicon, and then circuits are printed on these wafers. And then wafers has multiple chips or die on it. Once those circuits are printed, those dies or chips are sawed or cut into individual chips. And after that, those are assembly or packaged, put it in a casing. It's called packaging. And then final testing, and it's shipped to end customers, which may use those chips in a device. And then consumers buy those end devices.
One things, Saeed. You started with wafer and manufacturing. Take a step back, please, for us and make it alive. R&D, tools. There's a whole other slew in the value chain that happens before this process begins.
Absolutely right. So this is the manufacturing, or I call it the first layer of value chain. There are multiple layers behind it that makes this chip manufacturing possible. And to put a geographical lens also, so a chip, the IP for this chip could be designed in United Kingdom, using those IP and some of the design automation tools that could be provided by a company out of California. Chip could be designed by any number of fabless companies, could be in California. And then chips are those designed are shipped to a wafer fabrication plant. That wafer fabrication plant could be in Taiwan. And then its assembly and package could be in Korea, is stored in a warehouse in Singapore, and can be shipped for manufacturing to China, for end device manufacturing in China. And there are companies that supports, for example, software for testing. They could be based out of Israel. So there is a whole set of value chain that supports this manufacturing. And I gave a few examples of how these are geographically distributed. We did a study earlier on, and we found out that a chip through this process that I just described could travel 25,000 miles before getting delivered to final consumer. And it could cross border 70 times before getting to the end consumer. So the couple of things to note here. One, the value chain is spread across geographically, and there are multiple layers of these value chains. There is a manufacturing company that we see, and then there's a company supporting that. There are the companies that are providing raw material or software or solutions for that also.
I would love to emphasize this. An average chip, and this is from your Accenture report, Saeed, can travel on average 25,000 miles before it reaches the hands of an end consumer. It can touch 48 countries and cross 70 international borders before it touches the hand of an end consumer. And what I would like to make alive is the following. I think the way I think of the value chain, and I'm one of your electrical engineering friends, so I'll keep you honest, is, first there's design and R&D, tools. Then you need to do this big process of manufacturing in what we call fabs in the foundries. There's a lot of discussion right now because of concentration in Taiwan. And then there's assembly, test, and packaging. There's also this other layer of getting the raw materials. Where are those choke points? Where are those raw materials coming from? And then the final point, that this process of manufacturing in particular is very energy and water intensive. So I want to emphasize a couple of points with your knowledge. One on, just walk us down through, for every one of these stages, how complex is the value chain? What those interdependencies look like, what those choke points look like. And then we're going to talk a little bit about the resource intensiveness of this.
Yes. Let's drill down the wafer fabrication. When I described it, I said wafer fabrication process or printing the circuits on the wafer. That's overly simplified. I mean, that process alone has multiple layers of value chains supporting that. So first, you have a fab which has multiple machines or equipment that's going, whether it's deposition machine, etch machine, or lithography machines. Let's take an example of lithography machine. So that machine is provided for wafer fabrication by multiple providers. One of the most leading provider is a company out of Netherlands that does the lithography machines for very advanced chips. And for making that machine, they may need some very advanced laser or lenses. And that lens is provided by a very sophisticated company out of Germany. So now you can think about this thing. So a chip that is getting used in the phone, that chip is manufactured throughout this process of wafer fabrication, assembly, and packaging. For wafer fabrication, you use a foundry. They are in their fab using a lithography machine made by a company out of Netherlands. That company, to make that machine, is using lasers and lenses. The lens is coming from a company out of Germany. So you can see these layers. And this is just, we took lithography machine in a fab. There are hundreds of processes like this. In the fab, for wafer fabrication, for example, there is like chemicals you need. That chemicals are provided by companies out of Japan or US. Then there are some raw materials that are used, like substrates and some other raw materials also. Then there is to monitor the manufacturing processes. You need a specialized software. So that software is provided by another set of companies. For example, for yield management and things like that, that software could be provided by a company out of Israel. So I just wanted to explain this thing and highlight that we just took the overall value chain and took wafer fabrication, and within wafer fabrication took lithography and just expanded into multiple layers involved. So you can imagine how this broad and deep this ecosystem is.
Saeed, can I ask you to explain and draw the distinction between leading chips and legacy or mature chip technology?
Yes. So this is a good question. We refer to mature node, leading nodes, and we measured it in nanometers. So a lot of times you will hear, oh, this is an advanced chip, 5 nanometer chip. So the nanometer is basically the width or the size of the transistor on a chip. And that defines that how advanced chips is, how much transistors you can pack in a particular size of a chip. And nowadays we are doing chips which can have billions of transistors on one chip. The reason you can do billions of transistors on one chip because the transistor size has been shrunk into nanometers.
Moore's law.
Yes. I'll come to that in a second. So what's happening is this, what we call anything that is 10 nanometer or higher is generally considered a legacy node, and anything smaller than 10 nanometer or smaller like 10, 7, 5, and now 3 nanometer, those are considered advanced nodes or leading nodes. And when I started in the industry, like 65 nanometer was considered most advanced leading node. People were thinking, what's going to happen after 65 nanometer? But as Kirti mentioned, because of Moore's law, that we know that the number of transistors on a chip will double every 2 years. And that has been true for a very long time now. And the number of transistors are getting doubled because we have been shrinking the size of the transistors. And we are able to put, say, double the number of transistors on the same size of the chip every 2 years. So then, as the technology improved, we went from 65 to 40 to 28 to 14 to 10 to 7 nanometer now. So that's what I just wanted to give you that perspective. So anything 10 or smaller is considered nowadays leading node. And maybe when we'll talk about a few years from now, we'll say, oh, 10 nanometer, that's an older or legacy node. So whatever was the leading node of yesterday is now a mature or legacy node of today.
I thought it was surprising, Saeed, when you shared with me that 3 nanometer, that's a diameter that is smaller than the size of the coronavirus.
Yeah, yes. I mention this all the time. This is true. I mean, one is highly advanced manufacturing. And when we say we are doing manufacturing of printing of transistors at 10 nanometer, to put things in perspective, the diameter or the size of coronavirus is 140 nanometer, 140.
Oh, wow.
And so the coronavirus is 140 nanometer, and we are making chips at nowadays high volume production.
And 140 nanometer is like old legacy technology.
And 40 nanometer is like very old, we'll say. Exactly. So we used to measure this in micrometers, actually. Then we started measuring this in nanometer.
So, Saeed, it's really important that you have been able to draw a little bit of a picture of how complex this industry is. Incredible high-end technology and the most productized technology in the world, quite frankly. So, and also how globally intertwined the supply chain is. And that is leading to the concerns that, I was teeing up in the beginning of this conversation. Very high points of concentration, very high points of vulnerabilities in the supply chain. How did we get here?
Yeah, this is a great question. There are a couple of points that contributed to this. One, I think semiconductor industry, because of the volume of the number of chips that are made and the capital intensity that's required to manufacture the chip. Let's keep that in mind. A fab has always been a very expensive investment for semiconductor companies. To build a fab, advanced node fab nowadays could cost up to $5 to $10 billion. And even when the industry was maturing, this was a big investment. In the 90s, pretty much all the semiconductor companies were vertically integrated, had their own fabs. And actually, most of the semiconductor companies were part of the larger electronic companies. So for example, where I work, Motorola had their own semiconductor division, Motorola Semiconductor, which had their own fabs. Philips had their own semiconductor division, which also had their own fabs. So I'm just painting this picture to explain how, this industry evolved. Then later on, the semiconductor companies were spun off. They became their own companies. when you see NXP or Freescale came out of Motorola. And it was understood, or it was common knowledge, that if you want to have a semiconductor startup, you need to have a fab if you're going to be a semiconductor company. And it was a very capital intensive requirement. So that's number one. Keep that in mind. Number two is this. Around this time, late 90s, we were seeing a shift for outsourcing of manufacturing. And semiconductor companies also always solved for the best technology and the cost and the supply chain efficiency, and benefited from the overall globalization. So like any other high-tech companies, semiconductor companies also use globalization to solve for the cost, efficiency, and the technology. We see a lot of manufacturing, just like any other manufacturing, semiconductor manufacturing also moved offshore. At the same time, there used to be not a foundry business. There was contract manufacturing as it existed for electronic manufacturing, for printed circuit boards and things like that. But there was no outsourced contract manufacturing services for wafer fabrication. And then at that time, this also started. And at that time, there was fabless companies, because there was now outside contract manufacturing available. You can design a chip, you could be a fabless company, and then get the chips made by foundries. So this resulted in a bunch of fabless companies getting started.
Let's call them design companies for our audience really quickly.
Fabless only design companies. They will design the chips, but they will not manufacture chips themselves, because there were foundry company available to get the chips manufactured. And those foundry companies were offshore. TSMC started in Taiwan. And this resulted in actually a lot of manufacturing moving offshore to Taiwan, which was TSMC, the leading foundry company. So a couple of things happened. One, just a general move toward outsourced manufacturing that shifted like any other manufacturing, semiconductor manufacturing offshore also. At the same time, this concept of foundry and fabless, it used to be that you design the chip, you manufacture the chip. Now you can just design the chip and get it manufactured by a foundry. And that resulted in huge growth by TSMC also. So then this played out over last 20 plus years. And that's how the concentration of most of the advanced manufacturing, as Kirti was mentioning, is in Taiwan.
Kirti, I want to ask you, how can we get out of this? Can the United States become fully self-sufficient?
Yeah, so this is the conundrum now. I think what Saeed has drawn a picture for us is this period of intense globalization that many industries have experienced. Semiconductors is, I call it, the poster child of globalization that has benefited from this kind of a era that we lived in, where companies could set up operations, set up manufacturing, set up their plans according to the competitive advantage of different regions, and really do price optimizations, cost minimizations. And, that's why we saw, as consumers, prices falling for most of the products on the shelves for the last 40 years and low inflation, and we've enjoyed that process. Now, that era is over. Big theme in Davos this year was reimagining globalization. I think that we understand, Andrew, like you said, we need to get out of this, and we need to build some level of resiliency in the system to respond to other goals that we have in our optimization thinking, right? National security. We need to have fewer choke points in general in the globe. What happens if there is some sort of a takeover of Taiwan from China? How do we get the most important semiconductor chips in our products? But the reality is, I think no country in the world, nobody, including the United States, can be truly self-sufficient. The cost of that is simply too high. I think it's $1 trillion plus cost. So we have to live with some level of interdependency. But in order to get out of it, Andrew, I think things like the CHIPS Act, which are incentives that the government is providing to do some kind of a reshoring of the manufacturing onto the United States, need to work very strongly with our allies. We need to do friendshoring and reshoring in a way that is sensible, because Saeed described how many nodes and nanometers this technology traverses. We can't do it all. We have to rely on some things from our allies and other partners, and some things we can do ourselves. And we have to have some kind of a trade flow that stays alive.
I want to ask both of you, we see this tension between needing to do business with China, yet trying to become less dependent on China. Realistically, what can be achieved?
Okay, here's my view, Saeed. I think this is exactly right. China is both our biggest customer and a competitor, and we need to acknowledge that. So let me just, talk about some numbers here, Andrew. In terms of all of the net sales that originate from the United States for semiconductors, 35% of those end in China, meaning they're consumed by consumers in China. But when you look at the numbers of all the trade that passes through China as an intermediary, that number goes up to 70+%. So over 2/3 of all semiconductor trade that originates from the United States and ends in the rest of the world passes through China. In other words, those chips are taken into China, assembled into products, sent, then taken out and sold in different parts of the world. So it's really not restricting trade. We have to think about this. Like if we go too far too fast, we can actually kill the entire industry because you basically remove market access. Having said that, there needs to be some provisions, and I think the government is thinking about this, to be able to restrict trade in the right places where 14 nanometer and below, very high-end technology, so that the tech transfer can be limited and the United States can maintain its leverage points, its leadership in the most critical points in the value chain. But again, I would still exercise caution there and emphasize multilateral cooperation, because if we don't do it with other allies, we won't achieve our goals. Number one, because, those products and those technologies can be sourced from other competitors, foreign competitors, and they can gain the market share in China. And number two, we kill our own industry, the US industry, because now they have lost market share, critical market access, and then they don't have the money to invest in R&D and continue to be leaders.
Kirti, Saeed, summing up, give us one key takeaway for our audience.
I think the key takeaway is just important understanding of a couple of points. One, how semiconductors are so prevalent in our daily lives. We know about how much is used in technology, but in our daily lives. Second thing is this, how complicated this manufacturing is and how distributed this manufacturing is for chips around the world. So many players provide critical parts of the value chain for chips to actually finally get made and delivered to consumer. And there are multiple aspects of this value chain that are uniquely positioned in different countries and different regions. And they provide a very valuable and important part of the overall semiconductor industry.
Yeah, thank you, Saeed. I would just add that number one, most important fundamental technology. Number two, extremely intricately globalized. We have started a process of some level of deglobalization, but we have to recognize how far and how fast we can go is limited. And number three, as we enter this brave new world of some layers of deglobalization, as we call it, or reimagining globalization, let's understand that it is not cost-free. It has costs, it has to be done, but we are doing and should be doing a constant cost-benefit analysis. I think with that, Saeed, I really want to thank you for taking the time to talk with me and Andrew today. This is a part of a series that talks about the geotech wars. I think semiconductor chips are, as you said in the beginning, really the tip of the spear. And you really helped us draw a rich picture of the complexity that is underlying in the layer to make this chip a reality and give it to the consumers. Thank you, Saeed.
Thank you. It was my pleasure. Thank you.